Okay, we'll discuss our new topic called synchronous generators. Here, the basics, what are the topics that are there here? Everything, overview is displayed here. Okay, we'll try to discuss all the topics by the completion of this. It will be distributed in third units, fourth units, and half of fifth unit here. Parallel operation and everything here. Okay, so coming to this synchronous generators, at the starting we discussed that there are two topics are there here. In AC machines, in DC machines, DC generators and DC motors are there here. And similarly, in AC machines, one category is synchronous machines, another category is asynchronous machine. One category is synchronous machine, another category is asynchronous machine. Synchronous machine which rotates it only at synchronous speeds. Synchronous machine which rotates at only at synchronous speeds here. Okay, so Ns equal to 120 F by P here. Okay, which rotates at only at synchronous speeds. Asynchronous machine which rotates other than the synchronous speeds here. Okay. Last. Okay, just quickly copy this fast. Okay. Go for it. Okay, yeah. Again, in synchronous machine, it is subclassified into two topics here: synchronous generators and synchronous motors. We already discussed everything in the starting of the semester. Okay. So, what are the classifications of machines here? I guess now it is easy for us to understand here. Coming to asynchronous machine, which rotates other than synchronous speed here. There are two types here. Induction motor which rotates less than the synchronous speeds. NR rotor speed is always less than the synchronous speeds. Coming to the induction generator, we discussed in the last class. Okay, now. So by rotor EMF injection method and other methods, if you increase the speed to above the rated speed, the induction motor will convert now it as induction generator. Okay. Now it will rotate more than the rated speed, and here it will rotate less than the synchronous speeds. Okay. So everything we discussed, it can be used as for the power factor compensator, power factor improvement. We'll try to discuss in depth the concepts, everything in detail once we actually get into the main topics here. Okay. So we know this where we use this induction generators here. It is used in wind power generation because as wind speed is variable here always, it is not constant and fixed here. So we need a machine which can be used for a variable speed. Okay. So to be more specific, there is a name called DFIG, double-fed induction generator. Okay, it's an extension of induction generator. DFIG is nothing but doubly fed induction generator. So DFIGs are used nowadays. Okay, with the advancement of technology, DFIGs are used in wind power generation here. So can we expect that like fan, wind speed is always 70 kilometers per hour, 60 kilometers per hour, 80 kilometers per hour? So it always depends, it always varies here. So we are using a uncertain source for the power generation. For that we use the appropriate machine, that is DFIG or induction machines here. So there are two ways to generate the power here. Okay, we already discussed that. I have been saying the same thing from the last semester itself. To generate power, to generate EMF, what we require here? One is conductor, second one is magnetic field, okay, and third one is relative motion between 1 and 2 here. So out of this relative motion is I can able to generate either conductor rotating and this magnetic field is static, or magnetic field is rotating or conductor is static here. Okay, we already know this. In DC machines, the conductors are a group of conductors are rotating here, whereas magnetic field remains fixed here. Okay, magnetic field remains fixed. Okay, I hope you are noting down. Okay, simultaneously. Okay, so running notes is important. So these are the two options here. So in synchronous machine also, these are the two possibilities. These are the two possibilities. From the both the possibilities here, I can able to generate EMF. But which one I am selecting here? That is more important for me here. Okay. So which one I am selecting here? So in terms of power rating here, in terms of power rating, if the rating is below 5 kVA, if the rating is below 5 kVA, then similar to DC machine concept can be used here in synchronous machine. For a small rating, for a small power rating, we can able to use this rotating armature and stationary magnetic field here, because the armature weight will be less. It is easy to rotate the small rating application because small weight. So that similar to DC machine, we can make use of this concepts here. Whereas in real power plants here, the size of the generator or alternator, which is almost similar to double that of this room here. Okay, so it is vertically mounted. Let me try to tell you this also. Just give me 5 minutes of time. Why it is vertically mounted rather than horizontally mounted here. Okay, so when for a large rating machines, okay, number of conductors. Okay, so what we require here, power generation required more or not? We require less amount of power or more amount of power? If you see in Srisalam power plant here, it is written as 1100 megawatt into 6. What does it mean at the outside board? Okay, that means each alternator is having a rating of 1100 megawatts. That is measured in terms of active power. It is each megawatt is having a rating of alternate 600. And how many units are there here? 6. Only 6 alternators are there. Total Srisalam power plant, left bank or right bank. Okay, if I assume that near Telangana side, okay, it is 1100 megawatt into 6. I guess it's correct only. Approximately, you can assume that. Let's assume that. So 1100 megawatt into 6 units. So imagine how many conductors are supposed to be placed in alternator to generate 1100 megawatt of power. Very more number of conductors are required here. Okay, the size of the armature will be very high, or else size of the conductors will be more here. So in such cases here, which will be easy here? Rotating magnetic fields. Rotating magnetic field will be easy, because to generate a very high amount of power here, more number of conductors are required here. So I guess it's not ideal to rotate or move the very high or heavy weight conductors or armature. Okay, in such cases it takes more amount of energy, mechanical energy here. It's waste of. When we already have alternative. Okay, when we have already highway and one is fields. Okay, or else when we don't have any other way here, which is easy for us to cross from Narsapur to BVRT, obviously use the highway and directly come to BVRT directly by using any one of the vehicle here. What, Rajneesh? Yes or no? Okay, so that's only the easiest way. So when you have already alternate option, what is the option here? We have the option called, we can rotate the magnetic field here. So I will try to use the rotate magnetic field as a rotor and armature as a stator here. In synchronous machine, from now onwards we will be using two terms here. What is the two terms here? Stator and rotor. Stator and rotor. What? Stator is stationary part and rotor is rotating part. So by default, stator is now conductors. Okay, stator is conductors, group of conductors here. Rotor is nothing but magnetic field. Rotor is magnetic field. It is opposite to that of the DC machines here. Okay, obviously small rating machines we rarely use. Always synchronous generators we use for large rating machines only. Okay, so that by default here stationary field. Stationary armature, which is stator, and rotating field, which is rotor. I hope you understood now. Okay, in synchronous generators, why we go with this? Okay, stationary armature and rotating field. Am I clear? Shall I proceed? These are the two possible ways, out of which I'll go with the stationary armature and rotating magnetic field. Whereas in DC machines, armature is rotating and magnetic field is stationary. To be more specific, why I am going with this? Because we need to generate huge amount of power here. For that, we require more number of conductors here. It is very difficult to rotate a heavy object. Okay. It is easy to rotate a lightweight object rather than rotating a heavy object. So these are what are the advantages. So you can expect a question also. What are the advantages of stationary armature over the rotating armature? Okay, stationary armature over the rotating armature. So we have two options here. We have two possibilities here. We have two possibilities here. So out of the two possibilities, okay, out of the two possibilities, which one is better? Out of these two, which one will be better here? One is obviously stationary armature and rotating magnetic field, and second one is stationary field and rotating armature. Okay, comparing DC and AC machines here. Which one is better here? So obviously we can able to consider the stationary armature and rotating field for which case here? Synchronous machine. I am using a term called machine. What does it mean? It can be used for both for the generator as well as motor, like in the like similar to that of the DC machines here. Okay, similar to that of the DC machines here. So what are the here? High insulation AC winding is not subjected here. Okay, so for a rotating part here. Okay, let's try to concentrate here. If I assume that this part is stator. Okay, this part is stator. Now here I can directly connect three-phase supply. I can take inputs or outputs. For a DC motor, I have to give as an input three-phase supply. For DC generator, I will connect the power as output here. Is it easy to collect the power from a stationary part or rotating part? Which is easy? It's always easy to collect the power from the stationary part. That's why, okay, or else collect the power or give the power. But in case of both motor as well as generator here, both the cases, okay, it's easy to collect the current here. So that's why, so it's always easy to collect the current from the stationary part here. Whenever supply is there here, then automatically what happens here? In addition to that, voltage will exist here. Currents IR, IY, IB, and even line voltages, phase voltages will also be developed here. Line voltages and phase voltages also there here. Whenever voltages are there here, is it relevant to the insulation or not? Always make a blind conclusion here. Voltage is directly proportional to insulation, cable insulation. Voltage is directly proportional to cable insulation. That means if 230 voltage is I am using here, the insulation should be more than that, so that to withstand the breakdown strength here. Okay, so insulation is also easy here. Okay. Okay, main points is this one. It's easy to collect the currents and easy to deliver the currents here. Second one is rotating field makes overall construction simple because weight is less. As weight is less, it is easy to keep the magnetic field as a rotating parts. Whereas armature, which weighs very high because the more number of conductors are utilized, so that it is difficult to rotate a heavy object. Okay, and problem of sparking at the slip rings can be avoided here because armature, if I keep this armature as a rotating parts, okay, it will be like DC machine. In DC machine, what is the major problem here? Commutation will be there and sparkings will be there. Yes or no? All that things will again will occur here. Okay, and if you see that, if I assume this as a poles, field poles, this DC supply will be around some 200 volts and current will be some 50 amps. Let's assume that. Whereas stator current will be in terms of 100 amps or 500 amps. Okay, stator current is always more compared to the field current. So which is easy? High current should be kept at the stationary part is easy, or low current kept at the stationary part is easy. For rotating part, it's always preferable to keep the lower values of current at the rotating parts. That's why I am keeping this IF at the rotating side. IF at the rotating side here. So problem of sparking will also be avoided. If I keep what? Stationary armature. If I consider the stationary armature. Ventilation, it's not that much. And the DC excitation, yeah, whatever I said that. DC supply, excitation is nothing but, what does it mean? Excitation is nothing but field supply. Giving supply to the field winding. That we call it as excitation. Instead of all this, they will simply say that excitation, giving supply to the field. Okay, that is easy because slip rings, rotor fields, and let me try to summarize once again. Okay, let me try to redraw the diagram again here. This is stator. Okay, IR, IY, IB here. V. Okay, coming to this. Okay, and coming to this. Yeah, listen here. This one is rotor field winding. Okay, this one is rotor field winding. Now here, this voltage is some 200 volts. Okay, now here, if I consider rotor parts, if I consider armature, as rotating parts, if I consider armature as a rotating parts, how many lines and how many slip rings will be required here? Make a conclusion here. Split rings is used for which case here? DC machines. Commutator is also called as split rings. Slip rings is always used in AC machines. Slip ring induction motor. Yes or no? Slip rings is always used in AC machines. Split rings will be used in DC machines. Split rings, it is also called as commutator. Commutator is also called as split rings here. Now here, what's the purpose of this commutator or split rings here? So to transmit the power to the rotating parts. We can able to transmit the power to the, I'm just telling you the simple and easy words, not the textbook definitions here. We can able to transmit the power to the rotating part. For that, we can able to use commutator or slip rings. Okay, now commutator for DC machines and slip rings for AC machines here. Now here, if I use the armature as a rotating parts, now here we require R phase, Y phase and B phase and neutral. Total how many split rings or how many slip rings we use here? We require 4. We require 4 slip rings. Whereas if I want to, for which excitation is required, DC excitation is always preferable or not? At the last semester I told you that compared to AC excitation, DC supply is required because fixed polarity is used. If I give DC supply to the field winding, DC supply, then what happens here? North pole will be always here and south pole will be always here. Whereas if I give AC supply, what happens? For every 10 milliseconds, the polarity changes here. What I want here? I want a device to be permanent, similar to that permanent electromagnet, the maintaining a same polarity. For that reason here, DC supply is always preferable. It's simple objective bit here. Which supply is required or preferable for excitation? DC or AC? Which supply? DC supply. Why only DC supply is preferable? Why not AC? If I connect with AC supply, as per the hysteresis laws, okay, continuous magnetic reversal takes place here. So after some time, after 10 milliseconds, after the half of the cycle here, it will be changed to south pole. It will be changed to south pole here. So yeah. So now here DC supply. How many wires we require for DC supply? If I assume that magnetic field as rotating parts, we have one positive wire and one negative wire. So total how many wires we require here? 2. Just 2 is sufficient for us, which is easy. Keeping 4 slip rings or keeping 2 slip rings? 2 slip rings are easy here. So this also reduces the cost here. So in overall, we can say that. So easy to transmit the power, slip rings, number of slip rings will be reduced less and sparking will be less here and noiseless running operation and air gap will be length, it will be uniform. Okay, when magnetic field is kept in the rotor here and better mechanical balance. Okay, if I keep 10 kg weight in the corners of the three wings of the fan and if I start to operate in the middle, will the same weight will be maintained constant, will be there till the operation? It will definitely fall down because of the mechanical balance is not there here. Yes or no? Yes or no? Rather than that, if I hold some 10 grams of some wire, if I tie 10 grams of wire onto the three wings of the fan here, then obviously as the weight is less, it can able to hold till up to some extent here. Okay, so if I keep the low weight rotor at the middle or as a rotating parts, the mechanical balancing is also good here. Okay, ultimately all these motors machines will be operating 24 hours a day continuously. So we need this to be operating with good mechanical balance here. Okay, next. I hope you understood what are the advantages of stationary armature rotating field compared to the rotating armature and stationary magnetic field here. Okay, so at least out of this 6, if you try to can highlight 5 to 6 points, okay, so in depth, in points wise, with explanation, that would be better. So what are the diagrams that I have drawn? If you can include, just writing the points will not be helpful in getting the maximum marks. The 2 to 3 marks of difference will be helpful. You can able to get with the explanation. Okay. So insulation. Next, it's easy to collect or deliver the currents at the stationary parts. Next, construction will be simple and sparking will be avoided. Ventilation will be there, and number of slip rings with the rotating part. Number of slip rings will be less. Okay. Next, with the magnetic field is the rotating parts. Noiseless operation. Air gap will be uniform. Okay, and better mechanical balance. These are all the points relevant to the advantage of stationary armature over the rotating magnetic field. Coming to the next constructional. Okay. What is the conclusion here? We have concluded that DC field winding will be on the rotor. I hope we have discussed so many times why we have to keep DC supply. What actually happens? Let me try to add just in short. If I keep AC supply here as a then what happens here? So first half of the cycle it will be north pole and south pole. Second half cycle will be south pole and it will be north pole. Again third half cycle again it will be north pole and it will be south pole. Okay. Is this AC supply arrangement will satisfy our requirement? We want a permanent electromagnet which should be able to continuously generate magnetic flux from the north pole to the south pole. But by continuously alternatingly, when polarity changes here, it won't satisfy our requirement. That's why always field winding is excited with supply. DC supply. Right on the conclusion here. Always field winding is excited with DC supply. Okay. Always polarity is connected with DC supply, which can able to generate fixed polarity. Which can able to generate fixed polarity. Okay. With AC supply excitation, due to the continuous magnetic reversals, with AC supply excitation due to the continuous magnetic reversals, polarity always changes. Polarity always interchanges for every half cycle. Polarity always interchanges for every half cycle. Hence AC supply is not preferable for excitation purpose. AC supply is not preferable for excitation purpose. So yeah, we'll try to discuss the constructional details of alternator. Okay. Out of this, we'll only prefer stationary armature and rotating field. Here. Okay. So, what is that first part here? Stator. Okay. Stator by default. What we need to understand here, when it is stator, it is armature in terms of DC machines. Okay. Armature, group of conductors here. Okay. It is armature or group of conductors here. So how stator is made up here? It is made up of Okay, what material it is made up of is very important. Okay, what material it is made up? Rule number 18 absent. Okay, na? Okay, what material it is made up? Okay, that's very important for each type here. Okay, na? Whether it's stator or armature or shaft, only that material is enough here. So here it is made up of sheet steel lamination core here. Okay, sheet steel lamination. It is made up of steel. Okay, it is made up of steel, and laminations are done here. Why laminations are done? To reduce eddy current losses. To reduce eddy current losses. Laminations are done to reduce the eddy current losses. Okay, so notation. Okay, and you can see that in the diagram, you can try to remember the diagram approximately here. You can see that what are these? These are called here. These are called as slots. Slots at the outer periphery or inner periphery. There is a appropriate word here. As this is the total cylindrical in shape here, the slots are inner periphery. For stator, we always say that start at the inner periphery. That word should be specified and it should be highlighted. That's a major thing here. Slots should be made in the inner periphery for stator to accommodate the winding. It's similar to that of the DC machines here, to accommodate the winding here. Next. Next one is how the armature winding is connected here. Armature winding is connected in star connection. Okay. How the armature winding is connected? Armature winding is connected in star connection. Next. This is the corresponding diagram. Okay. So let's try to draw at the end. Okay. What are these? These are all windings here. I guess in the last semester we discussed single layer winding and double layer winding. What is single layer winding? If a single conductor is placed under the slots, then that's a single layer winding. What is double layer winding? If two conductors are placed under one slot, one at the top and one at the bottom, that's a double layer winding. So here it can be, as per the diagram, it's a double layer winding here. So if I want to generate more amount of power with the same available slots, I can go with the double layer winding, so that number of conductors will be increases. So this is approximate the practical diagram. Okay, stator laminations, laminated iron core. Okay, iron core with steel housing here. Okay. So I guess it's not required here. So basic things is slots are made, and in the slots armature windings are done here. Okay. What type? Okay, here it is laminated core here, and stator is assembly, and slots are made here. And in synchronous machine, we already said that what is the type of slot that are used here. In induction machines, we have discussed that there are three types of slots: open slots, semi-open or semi-closed slots, and closed slots. So semi-open, semi-closed used in induction machines. Open type slots used in DC machines and synchronous machines. Okay, which slots? Open type slots. Open type slots are used in DC machines and synchronous machines. Coming to the rotor. Rotor, there are two types of rotor. Similar to that of the induction, we have two types of rotor. And then as per the rotor only, we have classified as two types, spiral gear and slip ring. Similarly, in here also, there are two types of rotor here. One is salient type, just kindly note on here, first quickly note on. So this is salient type rotor, other one is non-salient. It's also called as cylindrical type rotor. Okay, salient type rotor, and the other one is cylindrical type rotor. So major differentiation will come only under the rotor. Stator will just to place the slots and accommodate the winding. Nothing we can get more than this. Okay, so two types here: salient pole type, and another one is non-salient pole type. Salient pole type, another one is non-salient pole type. So salient can also be called as projected pole, and non-salient pole can also be called as non-projected or cylindrical type. Okay, now you can ignore this smooth also, if not, it's not that much required. Cylindrical type rotor and salient type rotor. Okay, SALIENT. Okay, so first we'll try to discuss the first step here. That's it. First one is this is actually the diagram here, the better practical diagram. Okay, salient type projected poles here. Okay, what are the poles that you can see? That's okay, projecting outwards. That's why it is called as salient type. You're not expecting, okay, you don't need to draw diagrams like this in the exam, at least approximate relevant to this. Okay, so they'll by default questions, any unit, they'll ask you the first basic question is principle and construction. These are all very, very important. What, Teja? These are all very, very important. Okay, okay. So salient poles are nothing but, okay, for each type you have to write 5 to 6 points. That is more than sufficient here. Okay, from each topic we have to write 5 to 6 points. So what is the first point here? So it's also called as, okay, it is also called as projected poles type. Okay, salient or projected poles type. Okay, so here remember this is a rotor. Okay, when it is rotor, till now we used to assume that in DC machine it's a armature. Now we have to change our thinking that rotor in synchronous machine it is what? Field winding. It is field winding. Rotor, it is field winding. So for this field winding, is it a permanent magnet or electromagnets? Electromagnets. We require DC supply. For electromagnet we require DC supply, plus and minus here. So we all accommodate the winding and we'll get one plus and one minus for the excitation. Okay, to generate the flux here. Second one is poles are mounted on the larger circulars. Okay, we have the formula here, Ns equal to 120 F by P here. Number of poles, as per that we can able to get the synchronous speed here. So mounted on the larger circular frame here. Okay, it's a frame and out of that we can able to place the poles here. So how it is made up of here? This is important here. It is made up of thick steel laminations. It is made up of thick steel laminations. By default, whenever we come across the word laminations, you can add 2 to 3 points extra there itself to reduce the eddy current losses in the rotor. Previously, we discussed the laminations to reduce the eddy current losses in the stator. Now we are reducing losses in the rotor here. Okay. Now third point is field winding are connected in series. Next, ends of the connected with the DC supply. Total all the windings you can see that all the windings are connected in series, and we can able to extract the wires, 2 wires from outside, and we can able to connect the supply through which case here? Through slip rings, because the rotor is a rotating part here. The rotor is a rotating part. Next, what is the major thing here? The major thing here it is the diameter. Diameter is, okay, diameter is very high. Okay, and if you see this approximate diagram here, okay, diameter will be very high and length we call it as small l as axial length. We call the small length L as axial length. Okay, there are 2 terms here, diameter and axial length. Okay, so it's like this one. Okay, in cylindrical shape. Can anyone have water bottle? Yeah. So let me try to do this. So for this, though its diameter is less here, we assume that this diameter is more and axial length is less. If you see the other type here, here axial length is more or not? Okay, axial length for this is more, and this for this axial length is less here. So we can conclude that in which type? In sealant type. In sealant type we have less axial length than. In sealant type we have less axial length and more diameter. Okay, as per the example that I have shown in terms of water bottles here, less axial length and more diameter. Okay, less axial length and more diameter. We can get the corresponding thing in the reverse opposite terms in the second case here. Next, employed for where it can be used here. It can be used for lower speeds applications. This is more important, very important. Okay, why it is suitable for lower speeds? Can someone tell me? Why speeds has to be less? We already see this. How many poles are there here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So number of poles will be, for this type the number of poles will be more, as we have the formula n is equal to 120 F by P here. As more number of poles, synchronous speed will be less. Okay, as more number of poles, synchronous speed will be less here. Okay, simple. You have to explain this, then only you can able to get better marks. Okay, so for projected pole type rotor, we have more number of poles will be accommodated in the rotor. As there are more number of poles, as per the formula n is equal to 120 F by P, we can able to get less speed. So that's why it is suitable for lower speed applications. Okay, it is suitable for lower speed applications, and where it is as it is suitable for which power plant applications? It is suitable for tidal power plant applications. So in tidal power plants, hydro power plants, it is suitable. Okay, the speed required will be less. The speed required will be less here. So which type of rotors are suitable in tidal power plants? Salient. So many times asked. Okay, now. So in tidal power plants, as per the water head, we can able to generate the torque and will make the rotor to rotate here. So for this lower speed, the turbine will be lower speed applications here. So up to 300 RPM, not more than that. So for this case here, the particular suitable rotor is sealant type rotor. Okay, so projected poles will be there, and one of the major important thing is mechanically not well balanced. So mechanical balance is not better here, because what is the types here? Poles are where it is placed here? Outside. Due to the projected poles here, okay, all the poles are placed at the outer frame here, so that it is mechanically not well balanced compared to the other type, what you are going to see in the next case here. So these are all the points relevant to this. You have to draw the diagram. You have to completely draw the diagram. Don't expect everyone to draw the same, at least. So you have to draw projected poles, which definitely consists of 2 marks per diagram. And writing the other content will get you 3 marks. Even if the question is for a 10 marks question for each topic. Okay. Next. Shall we proceed? So already everything is shared to you guys. Nothing. Okay, let's try to. What we'll do here, we'll just discuss the damper bars where we actually place. We'll discuss its significance in the later classes here. Okay, damper bars. This is an easy diagram too. You can draw, so that even it is applicable even in the exams also. Okay, damper bars. Okay, this is the corresponding diagram. Projected poles here. How many poles we have? 6 poles here. Okay, so damper bars can be placed at the outer pole ships. Okay, at the outer pole faces. Okay, damper bars will be placed at the outer pole face. Okay, pole shoe. The other word is pole shoes. damper bars can be placed under the pole shoes here. Okay, so bars, a big bar, okay, damper bars will be placed under the pole shoes. So as it is in three-dimensional here, we can only see the front view. Okay, we cannot show you the complete three-dimensional diagram here. So what does it mean if I am placing here? Indirectly, the bars are placed like this. The bars are placed like this. Okay, where this damper bars are placed here, it is placed under the pole shoe of this projected poles here. Under the pole shoe of the projected poles here. So why the damper bars are placed here? It is used to prevent hunting. Just keep this word aside. We will discuss. There is separate 30 minutes class is required for this hunting concept. Okay. Separate 30 minutes concept is required for hunting concept. We will concentrate that. Okay. We will definitely discuss in detail. Okay. So with these damper bars here, we can able to avoid the hunting and we can able to generate the sinusoidal EMF here. We can able to generate the sinusoidal EMF and we can able to place the copper bars. Okay, that bars itself is how it is made up here. It is made up of copper. Okay, as of now, for constructional details, what we need to conclude that damper bars are used in salient pole type. Damper bars are used in the salient pole type. Okay, and it is placed under the pole shoes. It is placed under the pole shoes and it is made up of copper bars. And the main purpose is to reduce the hunting and to generate the sinusoidal EMF generation here. Okay, sinusoidal EMF generation, flux waveform. Okay, this is the approximate diagram. Okay, you can see that DC supply is connected here for the rotor and for stator. Okay, DC supply is connected. Everything is connected. All the rotors are connected in how? Windings are connected in series. Okay, and stator. These are all slots are placed here, and we can place the winding here. And three-phase supply is given to the stator. Either input for motor, output for the generator. Input for the motor and output for the generator. Next one is non-salient type. There is second type, non-salient type, or the easiest one is cylindrical type rotor. The other name is cylindrical type rotor. So cylindrical type rotor or turbo alternator. Okay, now. Okay, we'll just keep the second one, cylindrical type rotor. Why we are calling the other one, we'll try to discuss here. Cylindrical type rotor here. Cylindrical type rotor. Okay. So it is comparison. Okay, the previous one is suitable for low speed applications. Now this one will be suitable for high speed applications. Okay, when it is high speeds, what does it mean here? 120 ns equal to 120 F by P here. When it is high speeds, number of poles will be less. You can even add one more point directly. For high speed application, number of poles you can include directly. In this type of rotor, number of poles will be less. Mostly 2 or 4 here. For a 2-pole machine, what is NS? 3000 RPM. For a 4-pole machine, NS equal to 1500 RPM. Mostly either we will go with the 2 poles or 4 poles. If it is more than 2 or 4, it will be a salient type rotor. Okay, and speeds will be less here. And these features are important here. Okay, so as we discussed that diagram. Okay, this is the corresponding diagram. Okay, you can imagine that in backside, this is just a front view here. Backside, a three-dimensional diagram will be there here. As we see in the water bottle, water bottle can be considered as water bottle shape will be considered similar to this cylindrical type rotor, where this length will be, diameter will be less and axial length will be more. Okay, diameter will be less and axial length will be more here. Okay, axial length will be diameter will be less and axial length will be more here. So we have a relation actually. Always D equal to 6 to 8 times of L. L equal to 6 to 8 times of D. In case of cylindrical type rotor, competitive exam bit here. Okay, L equal to 6 to 8 times of diameter. Axial length. If D is value is given, what is the approximate axial length value? L equal to 6 to 8 times of D here. Similarly, even in salient type also. In salient type, the value is also given here. So in salient type, L value is already given here. D value is high and L value is less. Here I can say that D equal to 6 to 8 times of L here approximately. Approximately D equal to 6 to 8 times of L in case of salient type. Okay. So it is smaller diameter and less and larger axial length, and and it is we can able to generate less windage losses, and speed range is it is suitable for higher speed ranges. It is suitable for high speed applications. In which power plants high speed applications high speed requirements are there here? In thermal and in nuclear. Already in power system you might have studied this. Yes or no? Okay. In thermal plants and in nuclear power plants, where we can consistently we can get the input power here. Okay, so that it is suitable for high speed applications here. So that's why it is also called as turbo alternators. It's also called as turbo alternators. These alternators are specifically meant for the speed application, high speed applications, which is mainly used in thermal and nuclear power plants. Okay, thermal and nuclear power plants. Okay. This is the corresponding diagram. Is it in the similar shape of that water bottle or not? Where the diameter is less and axial length is more. You can see this. Everything is wedged. Okay. Everything is stiff and tough. Okay, now compared to the projecting type. Whereas in projecting type, mechanically it's not well balanced. Whereas here it is mechanically balanced. Mechanically well balanced here. Okay. Even that's why when it is mechanically well balanced, is it suitable for high speed applications or not? Yes or no? Is it suitable for high speed applications or not? So definitely it is suitable for high speed applications, shaft and everything. Okay. This is the conclusion diagram for salient type and cylindrical type. You can quickly draw these diagrams here. Okay. Here you can see that in salient type, actually for analysis, 4 poles are given, but it should be more number of poles here. P is more. Here P is less. Okay. Yeah. One more thing I forgot to add. Okay. In rotor, in cylindrical type rotor here. Okay. In cylindrical type rotor, okay, what actually happens here? Listen guys. Only 1/3 portion. You can see that only 1/3 out of this total circle angle is 360 degrees. If I assume this cylindrical rotor as front view as 360 degrees, only 1/3 will be used for the pole formation. 1/3 will be used for the pole formation. Next, rest of the 2/3 will be used for accommodating the field winding. You can add this point here. You can write this point here. In cylindrical type rotor, okay, in cylindrical type rotor, 2/3 of rotor. In cylindrical type rotor, 2/3 of rotor is used for accommodating the placing the field winding, placing or accommodating the field winding. 2/3 is used or accommodate the field winding. And 1/3 is used for 1/3 portion, 1/3 portion, 2/3 portion and 1/3 portion. 1/3 portion is used for the pole formation. Okay, this you can see the diagram here. This 1/3 is used for the pole formation. We cannot able to place. You are not supposed to keep the windings here. Okay, this is left empty so that a north pole or south pole will be formed. It will be formed, and as per that we can able to generate the flux. So this is how we can able to differentiate the two types of rotors here. Okay, so quick.